Welcome everybody at this presentation on the development of a CBA methodology for offshore grids. My name is Wim van der Veen. I'm working for DNVGL and I'm part of the Energy Market and Technology team in Arnhem, the Netherlands. Within promotion, I am task leader of work package 7.6 for the development of the CBA methodology. Besides DNVGL, also TenneT and Tractebel were involved in this work package. A first version of the methodology has been reviewed by several national regulators and ENTSO-E in a consultation procedure. Based on the comments, an updated version has been made and is now in the internal review process. The agenda for this presentation contains 3 topics. First, I will set the scene for the development of the offshore grid CBA methodology. The main part is about the challenges we face in comparing offshore grid alternatives, and they end with a brief summary of the presentation. Within promotion, a meshed European offshore transmission grid is investigated, connecting wind farms to shore. Such a meshed grid could provide significant financial, technical and environmental benefits. To understand the value to society of such a grid, a societal cost-benefit analysis can be useful. Existing SCBA methodologies are mostly designed to assess incremental changes to a system and are less suitable to assess complex systems that continuously develop in space and time. Therefore, there was a need to develop an SCBA methodology within the scope of the promotion project to identify the best offshore grid design. We call the best design the design that provides the highest value to society. This CBA methodology should provide a set of guidelines to value the benefits and cost of project alternatives based on inputs like scenarios. These benefits and costs are scored based on a predefined assessment framework. We started the development with a literature review into existing methodologies. There appears to be a common generic structure of these methodologies. This generic structure is defined through 7 so-called dimensions. What is the scope or purpose of the project? What scenarios can be involved? Which alternatives do we want to evaluate and with which key performance indicators or KPIs? How do we want to assess the KPIs and the overall value? Which tools are suitable and how should these tools be used in a KPI assessment? From this review, an initial guideline was defined for each dimension departing from the draft 3rd ENTSO-E guideline for CBA of grid development projects. The evaluation of the involved projects of common interest is already complex, but an offshore grid touches upon many more issues than a single transmission project. Based on the initial guideline for each dimension, a gap analysis was conducted between the initial guideline and the required features for offshore grids. This includes decisions on the level of complexity and discussions on assumptions and choices. This exercise resulted in both an ideal and a practical methodology. From an ideal point of view, the developed methodology should be applicable for a broad range of projects and should have a great level of detail for each dimension to accurately capture all possible effects and developments of offshore grids. The ideal methodology will be complex and time-consuming. To ensure the practical feasibility of the execution, simplifications will be required. 2 types of CBAs can be distinguished: financial and societal CBAs. Financial CBAs assess the financial value of a project, typically by monetizing all relevant indicators like project cost and revenues, to calculate the net present value of each considered project alternative. Guidelines are based around quantification and monetization of the indicators. Societal CBAs, in contrast, intend to assess the value of considered project alternatives to society. This not only includes monetary aspects, but also a broader set of societally relevant indicators. We further distinguish between a single project or a series of projects and a system that continuously develops over time, like an offshore grid. For a single project, usually a financial or project CBA is executed. The ENTSO-E methodology leads to a societal CBA for a single project or a series of projects. Combining the societal and system requires an extended societal cost-benefit analysis. As mentioned before, we define different stages of complexity, determined by what to take into account in the evaluation. Then a choice was made between the options. We did this for each dimension, starting with the scope. Besides the difference shown on the previous slide between financial CBAs and societal CBAs, we distinguish on the one hand value to society, value to each country, value to society and each country, and value to all stakeholders. And on the other hand, a non-monetized CBA, an augmented CBA, and a financial CBA. For promotion, the practical choice was to determine the value to society using an augmented CBA. For the scope of the project, it is also important to agree on the purpose of the project. Should this be only the offshore grid for evacuation of wind, or also the onshore grid for evacuation of wind, or should it also include market integration? For the practical methodology, besides the evacuation of the generated electricity by the wind parks, this will be market integration in line with the objective of the European Commission. Scenarios are required for various developments. This not only includes the definition of scenarios in the onshore markets, so-called land scenarios for the development of, amongst others, generation mix and fuel prices, but also the definition of scenarios in the offshore area, or sea scenarios. Also, scenarios need to be defined for used wind turbine technologies, for market design and grid development. For the offshore scenarios, a practical example of choices follows on the next slide. Scenarios should be chosen in such a way that it does not bias a certain project alternative over another. For example, if all sea scenarios have dispersed wind park locations, this might favor project alternatives with a lot of radial connections rather than meshed solutions. Offshore sea scenarios contain assumptions for wind capacity development in each considered future time step. For locations of this wind capacity, clustered in areas or dispersed towards the shore, and for wind turbine technologies that are used. In the ideal methodology, a certain number of variations for each parameter, capacity, location, technology of the sea scenarios should be included. However, from a practical perspective, this will lead to a non-workable number of alternative scenarios, in this case to 81 combinations. The choice was therefore made to use 3 scenarios for offshore wind capacity developments in the North Sea, with only a single, most appropriate, location and technology combination of wind parks. The project alternatives are the subject of the next dimension. To determine the project alternatives, it is important to agree on the purpose of the project and on which sectors and technologies are relevant. Do we only look at the electricity network or also at storage, and if so, which forms of storage? And which technologies do we take into account? Will only different topologies of electricity infrastructure be considered, or could possible alternatives also include other infrastructures such as the offshore gas infrastructure, storage, or power-to-gas options? What is ideal and what is practical? In the ideal methodology, a broad range of project alternatives should be compared, including alternatives with hybrid electro-gas infrastructure or storage, as this would help to identify the offshore infrastructure most beneficial to society. However, from a practical perspective, only a limited number of alternatives can be compared. In the practical comparison, possible topology options of electricity networks are recommended as promotion focuses on offshore electricity infrastructure. This will influence the outcome of the CBA. Important is to define the right project reference with which your project alternative is compared. In the ENTSO-E guidelines, each project is compared against one of 2 extreme baselines or reference grids. Projects can be included in the initial reference grid and are subsequently assessed following the take one out at a time or TOOT principle, or excluded from the final reference grid and are assessed following the put one in at a time or PINT principle. Comparison of large systems is not practical via this method. Such a system consists of many projects that are executed over time. Therefore, a base alternative or null alternative needs to be defined to which the others are compared. The promotion reference case or null alternative is a system with only radial connections. Another thing that is important for the CBA methodology are the boundaries for the project alternatives. Do we take the onshore development into account, and to what extent? In the practical methodology, we might assume the onshore grid can take on all wind energy without any enhancements. In the ideal methodology, full development of the offshore grid may be part of the project alternatives. For promotion, the project alternatives encompass the offshore grid infrastructure, including connection points with wind parks and the near-shore onshore grid. Guidelines are provided to define and determine the key performance indicators or KPIs. These indicators can be qualified, quantified, or monetized. The selected KPIs and their respective determination methods will affect the assessment framework and project comparison. Therefore, this should be done very carefully in order not to bias the outcome of the comparison. We agreed on a definition for each KPI and described the relevance of each KPI for the CBA. Starting point for this is the draft third ENTSO-E CBA methodology. The KPIs are arranged in costs, benefits, and residual impacts. Further, we discussed how the KPIs could and should be calculated both ideally and practically. Finally, we investigated the interaction of each KPI with other KPIs, especially to prevent double counting of effects. For instance, the KPI socioeconomic welfare interacts with the KPIs RES integration and CO2 variation. Question now is how to compare the project alternatives. For this, an assessment framework has been defined with guidelines. From an ideal perspective, each KPI should be expressed as much as possible in monetary terms, on the condition that objective monetization parameters can be obtained and that monetization is relevant. For each project alternative, the overall value to society can then be expressed in monetary terms, which allows for an easy comparison between alternatives. However, in practice, objective monetization is not always attainable or relevant for all KPIs. Therefore, some KPIs might be expressed in monetary terms, whereas others are reported in other quantitative units like megawatt hours or CO2, or even qualitatively. The aim in the practical CBA is to quantify and monetize the KPIs as much as possible. Comparison should be attained through multi-criteria analysis by assigning weighting factors to the KPIs and combine them into single value or, for example, a spider diagram. The best project will be sought through the importance that the involved stakeholders and project promoter will put on the different KPIs. Also, choices need to be made for the evaluation period of the offshore grid, the time steps for development, the time step of KPI evaluation, and related parameters required to perform the assessment of each project alternative. This includes the economic lifetime of components, the interest rate, and the residual value of the offshore grid. The recommended values from ACER, as adopted in the ENTSO-E guideline, will be followed as much as possible for both the ideal and practical CBA execution. Tools are important to quantify and monetize the costs and benefits. Network models evaluate the behavior of physical network flows and can help to quantify, for example, benefits connected with grid losses, adequacy, and security. Market models are required to quantify socio-economic welfare and also RES integration and CO2 variations. Three main aspects have to be decided upon in building the market model for the CBA execution. That is the geographical scope of the analysis, the scope of the onshore market model, and the scope of the offshore market model. Ideally, a lot of scenarios with a large scope would be simulated in the market model to get a broad picture on the comparison. However, market simulations with a wide scope tend to be very time-consuming, so limiting the scenario and scope is necessary in the practical execution. Also, the governing market design and bidding zone configuration are important to the result of the CBA, as the governing market design impacts certain KPIs. The governing market design, and in particular bidding zone configuration, will impact the development of the grid and operational strategies. These two impact in their turn the development, topology and operational strategy of offshore grid alternatives and the value of their KPIs. The choice of bidding zone configuration influences KPIs and the disaggregation of benefits. The market design might require changes depending on the considered offshore grid topology. However, the offshore grid topology that will be realized will most likely depend on the governing market design. There is a chicken or egg problem in that they are dependent on each other. Ideally, each project alternative should be assessed under different bidding zone configurations to assess the impact on KPIs. From a practical perspective, this will lead to a very large number of potential configurations, which are not relevant or likely to materialize for certain project alternatives. Therefore, a practical choice has been made to determine one appropriate bidding zone configuration for each selected alternative configuration. I would like to conclude this presentation with a few summarizing remarks. An improved societal cost-benefit analysis is necessary to understand the economic and societal consequences of offshore grids. A clear and objective methodology is required to compare alternative configurations in a transparent and unbiased manner. We have discussed a number of challenges in comparing offshore grids, like there's a lot of complexity in the CBA methodology for offshore grids. Valuing a single project is quite different from comparing complex systems. A pure financial CBA is not sufficient here. Societal impact also needs to be taken into account. Ideally, the methodology needs to take a broad range of projects and should have a great level of detail for each dimension. But in practice, simplification is necessary to limit the effort. Do we want full monetization or rather a kind of multi-criteria analysis? Eventually, the methodology must indicate the configuration deriving the greatest value to society. Thank you very much for your attention.